OK, so last time we introduced the Euler characteristic, which we won't do very much with this semester, but it's nice to have. So whenever this is, whenever the right-hand side makes sense, we call it the Euler characteristic. So if this is a finally generated abelian group, or at least if this is going to make sense, it's a finally generated abelian group. And so if you have HKM equal to z to the L plus t, and these are just elements of finite order, then the rank of HKM is L. So it's just how many copies of the free abelian group do you have? Right? And indeed, it is a dimension if you tensor this. So this is equivalent to the dimension over Q of HKM tensored with Q. Right? So you can get rid of all of the elements of finite order just by tensoring with Q, and then this becomes a power of Q, and you're just taking the dimension. OK, so this is a very nice invariant. It came up the first class when we were talking about the history, and Euler introduced this. An easy exercise using the fact that the Euler characteristic is a homotopy invariant is to show that there are only 5 possible regular polyhedra, right? The Platonic solids. OK. We also started talking about manifolds. So an n-dimensional manifold is a Hausdorff topological space. Let's call it M. Let's call it N because it's n-dimensional. With whose topology has a countable basis. And such that each point has a neighborhood U that is homeomorphic to Rn. Right? So these neighborhoods are called charts. These neighborhoods or coordinate charts, and a cover by charts is called an atlas. Okay. Great. So that's what a manifold is. And so we defined the local homology at a point is the homology of M relative to M minus the point. So if M is an m-dimensional manifold, then this is by excision the same as this for Rm minus the origin, and that is the same as the 1 degree less reduced homology in 1 degree less of the sphere Sm minus 1. And so it's just a copy of Z in degree m and 0 everywhere else. Right? So this picks out the dimension. And this tells us that the manifold is like uniformly of a given dimension. So that is to say, if you had something that wasn't a manifold that had, say, some conic singularities or something, then the local homology would point out where the conic singularity was. It's where the local homology would change. Okay, but in particular, since this points out the dimension, we got invariance of dimension, right, which is the theorem of Brouwer, and says that if M and N are homeomorphic, manifolds, then they have the same dimension. Okay, and then we started talking about the degree of a map. So if you have a map between spheres of the same dimension, then the induced map on the top homology is given by taking an integer and multiplying it by another integer, which we call the degree. Right? So this is the degree of f. Okay, so implicit here is that we have a preferred isomorphism with the integers, right? Because since you have two generators, you always have another isomorphism by just flipping the sign, right? So in order to make sense of this without any ambiguity, any sign ambiguity, we have to have fixed isomorphisms with the integers. So remember, we did this because we know that the reduced homology, which we might as well take, of the sphere is equal to the relative homology of the n simplex relative to its boundary, and we saw that that has a preferred generator, namely the identity map. Right? So that's how this is defined. And okay, and we saw that this has lots of very nice properties. This is a powerful invariant. In fact, everything that was proven by Brouwer, such as invariance of dimension, was done using the degree, which Brouwer introduced. This was a strong tool before homology was well developed. So we saw lots of properties, and then we started talking about the local degree. So if you have the good fortune to find a point in Sn whose inverse image is finite, then you choose ui and v neighborhoods of the xi and y respectively, each homeomorphic to Rn, and such that f of ui lands inside V, right? And then at each point xi, you have an induced map which also is a map from the integers to the integers, and it's given by multiplication with the degree of f at xi, known as the local degree. Right? And at the end of last class, I claimed that in this setup, the degree of f is equal to the sum of the local degrees. Okay, and that's where we stopped last time. Questions on last time? Yes?
This might be kind of a silly question, but can we have an example of an n-dimensional manifold?
The n-sphere.
Okay.
Yes, the n-torus. right? So a manifold, so say a surface is easy to talk about. So a surface, by definition, is something that locally looks like R2, right? So it's something where if you were standing on it, you could be excused for thinking that the world is flat, right? So, so of course, the sphere, the torus, or tori with more holes. Right? In all of these cases, if you're standing there, then you have a neighborhood where it looks flat. Right? So things that are not manifolds are, for example, if you have a cone, then everything looks fine over here. You have a nice neighborhood. But once you get to the singular point, it doesn't look right. Right? So yeah. So whether or not this is going to be singular actually depends on what is the cone over. If you take the cone over a sphere, it actually is smooth. It's not, well, it's not a singular point. But if you take, say, the cone on a torus, then it is going to be a singular point. In fact, as an exercise, compute the local homology of the cone over a torus at this point. And what you'll get is the reduced homology of the torus, not the reduced homology of the sphere. OK? So these are manifolds, and this is not a manifold. Yes?
What does it mean to take the cone over something?
So if I have the torus, then to take the cone, I cross it with an interval, and then I collapse everything at one of the endpoints, say it's 0. Right? So it means take the cylinder over the cone, over the torus, and then take everything, say, at the top, and collapse it to a point. Right? Or, as the picture would indicate, if you have it sitting inside some Euclidean space, then just pick any point not on it and add all of the line segments from any point here to the point. OK, more questions on last time? Yes?
Sorry, in that case, why is the cone over a sphere so
Right. So the cone over a sphere, it turns out that the singularity that you think you have is just cosmetic. So yeah, if so, sorry.
Does it become the disk or something?
So for example, the disk is a cone over its boundary. All right. So if you think of the disk and then you were to take the center point and just pull it up, it would look like a cone, right? So it is a cone. It's just that since it's called the link. Since the link is a sphere, it's not actually a singular point. So, or if you like, in terms of what I was saying before, if you were to compute the local homology at the cone point, you get the reduced homology of the link. So if that is a sphere, well, that's what you were supposed to get anyway for a manifold. Right? So yeah, it turns out it's not really singular. So Rn itself is an infinite cone over Sn minus 1. Yes?
What was the degree of function?
This integer. So you give me any function that goes from Sn to Sn. I look at the induced map on the top homology group, which is just a map from the integers to the integers. Right? And every homomorphism from the integers to itself is given by multiplication by some integer, right? So that integer we call the degree. Okay, more questions? Yes.
So you say that we can tell the cone of a sphere is still a manifold by the fact that if we compute the local homology at that point, we get what we should get.
That's a stronger statement than I want to make. So that's supporting evidence for the fact that it's a manifold.
Right.
Yeah. So you show it's a manifold by showing that you have coordinate charts.
Okay, so
Yeah.
so that answers my question then. Which
Yeah.
was, can you just use local homology? Or do you need
No.
more?
Yeah, you need this. Yeah. Yeah, so there's a whole class of spaces called homology manifolds. So they're not actually manifolds, but the homology behaves just like four manifolds.
Can any of them be cell complexes?
Yeah.
Okay.
More questions? Okay. So let's prove this fact about the degree being the sum of the local degrees. Okay, so to get the degree, we should look at the induced map here. Now, we can include the complement of y into here and include the complement of the inverse image of y into here, and we'll get a commutative diagram. Right? It's a commutative diagram because it commuted before you took homology, right? The inclusions and the maps by f. So when you take homology, it's still a commutative diagram. The top arrow is given by multiplication by the degree of f. Here, we can use excision to write this as a direct sum of these ui's. Oh, I don't know if I said over there, but I hopefully said this last time. We can choose these so that each homomorphic and the ui's do not intersect. Right, so you have these finitely many points in a Hausdorff space. You can certainly pick small enough neighborhoods so they don't intersect. So then you can use excision to write this as the homology of the disjoint union of these neighborhoods. And then the homology for disjoint union is just a direct sum of the homologies. Right, so this is OK, so each of these is a copy of z. Right, so this is just direct sum of z's. This is z. So all we need to justify is that the induced map by f here gives you the sum of the degrees, the local degrees. Right? So we know that that's what f is doing from each of these. Right? So I can also write this. If we want, we can write this as hn of v. Oh, I don't want to do that. No, I want to leave it like that.
Okay, sorry, I'm a little bit confused about what's going on. So we're trying to show that the degree is the sum of the local degrees?
That's right.
Can you say again what the local degrees are?
Sure. So we have these neighborhoods, right? Ui is a neighborhood of xi that is homomorphic to Rn, right? So that means that if I compute the local homology using ui, I just get the integers, right? So f induces a map from each ui into v that maps xi into y, and so it induces a map from the relative homology to relative homology. Each of these is just a copy of z, and so it's just multiplication by some number, right? That number is the local degree.
Okay, and then over here, what exactly are you trying to do?
So we have the map on top, which is multiplication by the degree, and we want to relate this to the local degrees. So we do that by including this into the sphere, right? And then, actually, probably over there I wanted relative. Yeah, OK. Sorry, this should have been relative. OK. Yeah, otherwise it would have been 0, because if you take away 1 point from a sphere, it's contractible. OK, so we have this relative. And so the local degree is just the sum, is just the map that you get induced in each of these factors, right? So the only thing we have to justify is that the induced map on the direct sum is just the sum of the induced maps, okay? Which of course it is, but we'll justify it by drawing a big diagram. OK? So the claim is that this map on the bottom is the sum of the local degrees. Okay, so here's a diagram. So let's put hn of this one here. Right, which we would call is the direct sum. Okay, so we have a map. Okay, and then each of these we can map across using F star. Okay, so we fit this into a larger commutative diagram. I also have an arrow going this way.
How do you know to write this diagram?
It's not so bad, actually, because what we want to know is what's happening to these individual factors, right? The individual summands. And notice this map is just the inclusion of the jth summand. And this map is just a projection onto the jth summand. Gesundheit. So adding these is very natural for trying to figure out what's going on with each summand. And then once you have these, this is just act on it by f, which is what you're trying to figure out. Right? So it's not Gesundheit. It's not actually a very mysterious diagram once you've drawn that one. Okay, so this is an isomorphism. Gesundheit. It's an isomorphism by excision, and so is this one. Yes?
This might be a trivial question, but is there a reason you're using different subscripts J and I?
Oh, sure. So I'm taking the sum over I, right? So this is going over all of them, and then J is a particular one, right? So for each J, I have such a diagram.
Wait, how did you get at the isomorphism?
Gesundheit. By excision.
And then what are the arrows going up?
This is just from the long exact sequence in homology. So is this one. This is long exact sequence in homology. And the, so this is a pair Sn minus xj, Gesundheit. And Sn minus xj is contractible, right? If you take a sphere and remove a single point, then that's, you can contract that to the opposite point, for example. Right? So that makes this arrow and this arrow also an isomorphism, right, from the long exact sequence. Okay, so we know that 1, we identify this with the integers, and we know that 1 gets sent here to the degree of f. So we're just trying to figure out what happens in the rest of the diagram. So we want to figure out what happens to 1 under this map. So well, we know that if you go this way, you get 1. 1 goes to 1. Right? Because we have an isomorphism, and this is our preferred generator gets sent to our preferred generator. But this map is just the projection onto the jth factor, right? So when you take this and you project it onto the jth factor, you get 1 for any j, which means that the image of this going up has to be the vector that just has 1 in every component. Right? So here 1 going up gets sent to 1, 1, 1.
Wait, why is that true?
Yeah, so I want to know what happens to the jth component here, right? So, but I can see the jth component by going up and then projecting onto the jth component, right? But that's the same as going this way, and I just got a 1, right? So you get a 1 in each component.
You could have anything there as long as the j component is 1, though, right?
I could have anything there as long as the jth component is 1. That's right. But since it's true for every j, all the components are 1. Yeah. OK. Then here, this is just the inclusion. So this takes 1 and sends it down to 0, 6, 1. There's a single 1 in the jth factor, right? And now here, this 1 would get sent to multiplication by the local degree. Right? Which means that when you have a 1 in the jth factor, sorry, this is xj, a 1 in the jth factor would get sent to multiplication by the local degree at xj. So that means that if you have 1 in every factor, this gets sent to the sum of the local degrees. OK? So we win. Right? So then this map is the same as this map, which is the sum of the local degrees. OK. OK. So let's check that this invariant is non-trivial. Example, if you go from S1 to S1, so we saw this last time. Think of this as sitting inside the complex numbers. And then just look at the map that sends C to Z to the K. Right. Then this has degree K. So how do we know? Well, for example, take the inverse image of 1, and you'll get the kth roots of unity. Right? So F inverse of 1. You have the kth roots of unity, and then if I look at, say, the segment, if I split the circle up into k segments of equal length, then when I act on them by f, each of these will be stretched out to cover the whole circle. Right? So the local degree at each zeta j is 1 if k is positive and minus 1 if k is negative. And then when you sum them, you get k. Well, minus, yeah. Hence, the degree of f is equal to k. Okay. So that's true for k positive or negative. Right? OK, great. So for S1, there is a map of every degree. So now to do this for Sn, there's a trick, which is to suspend. So recall from chapter 0, the suspension of a space is what you get from taking that space and then coning, say, up and coning down. Right? So you can think of this as x cross 0, 1, where we're going to collapse everything at 0, and we're going to collapse everything at 1. You can think of this as the cone on x, two copies of the cone on x glued together at their base. You could also think of this as the cone on x where you collapse the base.
What did you say we call this? Like,
The suspension. Okay, and of course the point is that if you suspend a sphere, you get the next sphere. Right? Because you're just adding the upper hemisphere and the lower hemisphere along the equator. Okay, so now any map induces a map between the suspensions. So if we think of the suspension as equivalence classes in x cross the interval, right? So you have a point x and something in the interval, you just send that to f of x, the same point on the interval. Right. So this is, of course, a well-defined map from x cross the interval to y cross the interval. And so to make sure that it descends to the quotient, we just need to make sure that all the points that get identified get treated the same way. But everybody who lives above 0 gets sent to somebody comma 0, and all of those points get identified. And same thing, everybody that lives above 1 gets sent to something comma 1, and all of those points get identified. So it's a well-defined map. Yes?
Is there, equivalence class.
Yes.
I was trying to figure out why you were using square brackets.
Yeah. Okay, so here's a lemma. If f is a map from Sn to Sn, then the degree of f is equal to the degree of the suspension of f. Okay. Okay, so the thing to note to make this work is that if we have such a map, then this also induces a map cone f from the cone to the cone, right, by the same reasoning. And so we have a nice little commutative diagram. So I can think of the suspension as being the cone where you've collapsed x. And so this is the quotient map. And the induced map on the cones commute with the induced map on the suspension with the quotient map. Right? Because you're just taking everything on the base and collapsing it to a point here, collapsing it to a point here, and so this map and this map commute. Okay, so this.
What are the maps going down there?
The quotient map. So just the collapsing.
What letter?
Q. Sure. So if you just think about what the maps are, so both of these maps are induced from looking at x cross the interval to y cross the interval, right? And then up here, all you're doing is saying everything comma 0 gets identified. So that's great here, and that's great here. Here, what you're doing is you're saying everything comma 0 gets identified, and everything comma 1 gets identified, right? And this map is just the one that identifies everything comma 1 to a single point, right? Sure. OK. So now we just look at the pair cone x comma x, where you have cone x, and then here's x, right? So the base, right? Well, of course, we're doing this for the sphere. In particular, this is a good pair. And so the relative homology is going to be the homology of the quotient. And the quotient is the suspension. Right? So we look at the long exact sequence. And here is the relevant piece. Well, actually, whatever. hk plus 1 of the cone on Sn. We map this to hk plus 1 relative, right, which is the same as the reduced homology of the suspension. hk plus n. And let's do one more term. OK, and then I have the same thing. So f maps down Yes.
So the relative homology there is the same as the homology on the sphere because it's a good pair?
Correct. Yeah. OK. I'm not sure how much I've emphasized it, but the fact that this is a commutative diagram is something called naturality. So commutes by naturality. OK, so what naturality means, well, of course, there's a technical meaning. There are natural transformations in the background, which is why we call it naturality. But to avoid going into that at the moment, what naturality means is that every time we did a construction like you have a space, you get singular chain complexes from the space. Or you have a short exact sequence of complexes, you get a long exact sequence in homology. Those constructions are natural in the sense that if you have a map between the objects you started with, then you get a map between the objects you end with. So if I have a map between topological spaces, then you get a map between the singular chain complexes, right? And because it's a map of complexes, that we're including the fact that it commutes with the boundary map, right? If you have a short exact sequence of complexes, and then another short exact sequence of complexes, and a map between them, maps of complexes, so really that means a bunch of commutative diagrams, then each one of the short exact sequences gives you a long exact sequence in homology, and the maps between the short exact sequences will give you maps between the long exact sequences homology, right? So it is not at all hard to check. It can be complicated. There are lots of diagrams to draw, and so I'm not going to do it because it would take some time. I encourage you to do it by yourself or to look it up in Hatcher.
So this naturality thing is in Hatcher?
It is.
Okay.
Yeah. OK. So, but in any case, this commutes. Okay, and if I take the cone over a space, then that's contractible, because you can just retract everything to the cone tip. Right? So this is going to be 0, this is going to be 0, and also here at the end it's going to be 0, and this is going to be 0. So, well, and here I really put too many arrows. There's a single arrow here. So this says that you have an isomorphism of well, I should have put reduced. You have an isomorphism, here also reduced, whatever, between the kth reduced homology of Sn and the k plus 1 of the suspension, and that isomorphism commutes with the action of f star. Right? So in particular, if you look at the top degree, then this is going to be multiplication by the degree, and this is going to be multiplication by the degree.
Why are you looking at the reduced homology?
The long exact sequence, I can always take reduced homology, and when I have a contractible space, it's the reduced one that's always 0.
Okay.
Right? So if you don't put reduced, then you have to say, or when this index is 0, you have a z. Okay, so that proves that the degree of a map and the degree of the suspension are the same. And since for S1 we have a map of whatever degree you want, then for Sn we have a map of whatever degree you want. Just suspend until you get there. Okay. Right, so
Wait, so is that the end of the proof?
that is the end of the proof.
Sorry, I don't see where the confusion.
Sure, so it's here because this commutes. So as this commutes, setting k equal to n, we have we have here multiplication by degree of SF, and here we'd have multiplication by degree of F. So these degrees are equal. Yes?
I'm still confused about the introduction of the reduced homology some places, but not every place on the.
Well, these are relative groups. You can put reduced or not, and it's the same, right? So relative groups, whenever the subspace is not empty, there's no difference between reduced or unreduced, right? Directly from the definition. Yeah, otherwise, well, every time you have a long exact sequence in singular homology, you have a long exact sequence in reduced singular homology. So it's just up to you which one you use. But reduced is convenient because then you don't have to make distinctions for the zeroth group. Yes, more questions on this? Okay, so one thing that's in the background here when we're talking about degrees that has only come to the foreground once, which is when we were defining delta complexes, is the notion of orientability. So I thought it'd be good to talk a little bit about orientability before moving on. In particular, to talk about how you define the degree of a map between manifolds that are not necessarily spheres. So let's talk a little about orientability. So specifically, when is a manifold orientable? Yes,
Can I ask a question?
please.
In what cases is this like extendable to general spaces? So if some space has the same homology groups as the sphere, then can this proof be applied?
Yeah, so, yeah, I don't see that we used anything. What would be different Yes, so the proof would work exactly the same, and the homology groups of the suspension are going to behave well, just like they did for the sphere. What's going to be different is that you're going to leave the class of manifolds. Right? So if you suspend something that's not a sphere, that won't be a manifold. Right? Because the two cone tips are not going to behave the right way. Yeah. But otherwise, yeah, the proof goes through just fine. Okay, so at each point, a choice of generator of Hn, so it's called manifold M, M minus a point, is, well, let's give this a name too, mu of P. A local orientation at P. Okay, so a manifold locally looks like Rn, right? Rn, we know how to orient. You pick a basis, and the order that you picked on that basis gives you an orientation. There are two possible orientations, right? So if you flip the order of two contiguous elements, you get the other orientation. So here, at every point, we have this, and this is like the homology of Rn minus the origin by excision. And we have two choices of orientation, which are just the two choices of generator of this group, because it's the integers, and you could pick 1 or minus 1. Right? So you might think, well, why don't you just always pick 1? And that's fine. If you're doing local orientations, you can do that. Just always pick 1. Just always orient Rn the usual way. And that's how what we did to define local degree. Right? But the problem is, if you want to pick a local orientation at every point, and you want to do this consistently, then you don't always get to choose what you're going to do at every point. Right? Really, if you can think that if you orient at a point, then nearby points inherit an orientation. Right? And so you can think of your manifold as being put together by these charts. And then the problem is, OK, if I pick an orientation at this point, and then keep looking at what happens at each chart, when I come back to this point, do I get the same induced orientation or not? Right? OK, so then we want to be able to say whether or not two orientations at nearby points are consistent. So if U is a chart on M, so remember that just means that it's homeomorphic to Rn. And PQ are in U, then orientations mu P and mu Q are consistent if they correspond under, OK, so you could look at the relative homology no, let's do this. M minus P. You could look at the relative homology M minus Q. And I don't have a map between them directly, but I do have isomorphisms from excision with M minus U. So if I give you a generator here that chooses a generator of this group, all of these are the integers. So if a generator here chooses a generator here, chooses a generator here, so they're going to be consistent if you get the same one, right? If mu P goes to mu Q.
Can you say more on what it means for these to correspond?
Yeah, so since these are isomorphisms, I can reverse one of these arrows. And then I get a map between one of these groups and the other one. So if you identify them with the integers, then you're either sending 1 to 1 or 1 to -1, right? So they're going to be consistent if you send the generator here to the generator here.
Okay.
In other words, if 1 goes to 1.
If 1 goes to 1, well, I mean, here you might have chosen, I mean, we've fixed generators, so you might have chosen -1, all right? So, but yeah, so if 1 goes to 1, where 1 is the generator here. So then a global orientation, or just an orientation, consists of two things. On the one hand, at each P and M a choice of local orientation. In P, and then an atlas of charts such that whenever P and Q are in the same U alpha, mu P and mu Q are consistent. Okay, so a covering by charts where all of these orientations are consistent, right? So again, you could think that you're choosing an orientation. I give you a point, right? And you choose a local orientation at this point, right? By this diagram, that gives you, if you pick a coordinate chart, that gives you a local orientation at any other point here, right? Because you can identify any other local homology group with the homology group with the whole, using the whole neighborhood, right? So this orientation, pick the local orientation at every other point in this neighborhood, right? So now you could take one of these points and choose a chart around it, right? And since you've already chosen the local orientation there, that gives you the local orientation everywhere here, right? So the only thing you have to worry about is that if you keep doing this, then when you come back around, this choice induced a choice back here. That better be the same choice, or we have problems, right? So if you can choose these charts, and well, basically it's the charts. So if you can choose the charts so that there's no problems. Every time you come back around, you're back where you started, then the manifold is orientable, and if not, not. So as an easy exercise, check that the Mobius band is not orientable.
And then for synthetic homology, doesn't need local orientations don't need to be the same.
I'm sorry?
For synthetic homology, when we were doing the orientation.
Right. No. So yeah, we never asked any sort of global orientability. Yeah, we were just saying, okay, every time you use a simplex, you're using a oriented simplex. Yes.
How I like see like what would go wrong. You're saying it's an easy exercise to check.
Yes.
The Mobius band is not.
That's right.
So I see like why like if you tried to pick these local orientations, then it like wouldn't work. But how would you show that you can't?
Right. Well, so that's why I leave it as an exercise, because I think you'll get useful intuition from trying to show it.
Okay.
Yeah. But if you have problems with it, let me know.
Okay.
Yeah. So also RP2 is not orientable. The Klein bottle is not orientable. Yes.
So if a surface, or not just a surface, if a manifold is not orientable, can we always find sort of a circle of neighborhoods like this with this property?
Yes.
Okay.
Yes.
So what points come to a smooth manifold? Does this definition equivalent to the normal definition of orientation?
It is. It is, yeah. So I'll say a little bit more about that today, probably. Okay. Anyway, that's what it means to be orientable. So next semester, we'll prove the following fact. If M is compact connected manifold, so no boundary, in particular no boundary, isn't it? Then H and M is the integers of dimension n. Then this is the integers if M is orientable, and 0 if not. Okay? So if you have a compact and connected manifold, then orientability completely top homology group. Okay? So if M and N are compact connected manifolds, well, actually, I don't care. If they're, well, this connected, orientable. Right. So vocabulary. Orientable means that such a choice is possible. Oriented means that you've made a choice. Are compact connected orientable manifolds of the same dimension. Then any F between them induces a map between the top homology groups. So an orientation gives you an isomorphism with Z. So this comes from choosing an orientation. Right. So if you choose an orientation, then these both become just copies of Z. And so this map is multiplication by an integer, right? Unambiguously defined integer. And we call that the degree. Wait. Okay. If you were to switch orientations on one manifold, then you would change the sign of the degree. Right. So it's really an invariant of oriented manifolds.
Are we going to show that Hn of M is the if M is orientable?
Next semester.
Okay.
Yeah.
Oh, right.
Mm-hmm. Not that we couldn't do it now, but just for reasons of timing.
Are we allowed to use that, or?
Well, this is really a digression, so this won't come up.
Okay.
But in life, sure. This is true. Okay. And again, if you're in the fortunate setting, if y in n is such that f inverse of y is finite, then you get local degrees, and the degree of f is equal to the sum of the local degrees with the same proof. Just replace the spheres with oriented M and N.
I think last time you said something about like we're always able to find a point where f inverse of y is finite.
Glad you asked. Yes, so the next thing I wanted to mention was why is this a reasonable thing to hope for? Okay, so why is this a reasonable way to compute? Okay, so let me make sure I don't skip something. Okay, so for arbitrary manifolds, the way we've defined them, they just have a topological structure, right? So you can do a lot with the topological structure, but you can't do everything. If M and N are smooth manifolds, So all of the examples we have of manifolds are actually smooth manifolds. Technically, what this means, so every coordinate chart looks like Rn. So we know what it means to be smooth on Rn, right? It's a smooth map on Rn. It's what we teach our calculus students, right? So just infinitely differentiable. So every manifold, every choice of chart tells you what it means to be smooth near that point. But that's only a good definition if different charts give you the same notion of smoothness. So what you have to watch out for is that when charts overlap, so you have a map from Rn to Rn, that should be a smooth map. Right? So these are called transition maps. So if every transition map between overlapping charts is smooth, then you say that your manifold is smooth. And then it makes sense to talk about smooth functions on the manifold. Okay? So if you have smooth manifolds, then it makes sense to look at well, tangent spaces. Every point has a tangent space. And any smooth map induces a map. Well, it has a derivative. It takes the tangent vectors at a point to the tangent vectors at the corresponding point. Okay? So in local coordinates, you're just looking at Rn. And in local coordinates, so this is just some map from Rn to Rn, and this is just the Jacobian of that map. Right? So this is just the Jacobian in local coordinates. Okay, so say that y in n is a regular value of f if at each x in the inverse image, the map is surjective. Okay, so look at all of the points where this Jacobian matrix has full rank. Okay, those are called regular values. So at a regular value, because you have full rank, you can use the implicit function theorem, which is a fantastic theorem. So one thing that the implicit function theorem tells you tells you, for example, that the inverse image of y, so if y is regular, then the inverse image is a submanifold, smooth, of dimension equal to the dimension of m minus dimension of n.
They're inverse functions.
They're the same, but sure. So you get a smooth submanifold of the dimension given by whatever it has to be. And in particular, if dimension of m is the same as the dimension of n, and m is compact, then the inverse image of a regular value is a submanifold of dimension 0. And because this is compact, it's a finite set. Moreover, f restricted to ui from ui to v, where I'm using the same notation we had over here, So this would be, so ui contains xi, y is contained in v, and ui and v are charts with ui intersect uj empty if I is different from j. Moreover, this is a diffeomorphism. Okay, so this is the situation I was talking about last time. So if you have a regular value and the manifolds have the same dimension, then the inverse image is finite and you have a diffeomorphism between neighborhoods, right? So as we saw, a homeomorphism has local degree either 1 or -1, right, because it has an inverse. And a diffeomorphism is a homeomorphism, so it has local degree 1 or -1. So you just count the inverse image of a regular value with a sign. If this restricted map preserves orientation, then you give it a +1, and if it reverses orientation, you get a -1. And moreover, how do you know if it preserves or reverses orientation? Well, if you pick your atlas with oriented charts, so pick an atlas from your orientation, then you have these Jacobian matrices, right? Take the determinant. If it's positive, then put a +1, and if it's negative, put a -1. So everything is wonderful as long as we have regular values, right? So here's a fantastic theorem, Sard's theorem, although in this case it was proven by Brown, which says that the set of regular values is dense in N. So if you pick a point at random in N, it's a regular value. So that's why this is a perfectly good procedure for making this work. In practice, you don't pick a point at random. You pick a point, and if the map doesn't work, then you homotope it a little bit, and then it works. Yes?
What is N? Is it just a general?
Yeah, it's just a smooth manifold of the same dimension as M, and at this point now it's oriented.
Okay.
Well, for this I don't need oriented, but to compute the degree, I would want it oriented. Right? So that's why I said that this was a reasonable thing to do to compute the degree, because that's how you do it in practice. And then we already saw many instances of how the degree is a powerful invariant. But since I've already told you about smooth manifolds, let me give you one more application. So let's suppose that you have M is an n-dimensional manifold with boundary. And M sits inside Rn. Okay, so maybe I won't give you a precise definition of manifold with boundary. It's what you think. So for example, take the torus and now fill it in so that you have the whole donut and not just the frosting. That's a manifold with boundary. And that's a three-dimensional manifold sitting inside R3. Right? So that's exactly the situation I want. Take an n-dimensional manifold with boundary sitting inside Rn. Okay. At the boundary, let nu be an outward pointing vector field. Right? So this is just like in calculus when we're teaching our students about how to integrate. You pick an outward pointing vector at the boundary. Right? Right, so let's make it have unit length so that it defines a map from the boundary to Sn minus 1. And if we assume that everybody is oriented, then this has a degree. Okay. Now remember, one of our applications of the degree last class, which I realized was before the break, so a long time ago. But one of the applications involved vector fields, right? And what we said was, if you have a vector field and you have an isolated 0, then you look near that, and since it's isolated, then there's a disk where you don't have any other zeros. And so you can normalize it on the boundary of that to get a map into the sphere, right? So we're going to do that here. Take any, let V be any vector field on M. Let's have V equal to nu on the boundary with isolated zeros. And so let's say 1 to PL. Right. The index of V at a point Pi is the degree of V restricted to the boundary of, say, UI divided by its size from Sn minus 1 to Sn minus 1. So this is what I just said. If these are isolated zeros, then each one of them has a little neighborhood with no other zeros, right? So, and that neighborhood is, you can take to be a coordinate chart. So its boundary will be Sn minus 1. Right? And so if you normalize so that it always has unit length there, which you can because there are no zeros, then you get a map from Sn minus 1 to Sn minus 1, and you can take the degree. OK? So here is an awesome theorem. Poincaré-Hopf. The sum of these indices is equal to the degree of nu. So that's already really cool because it tells you that it doesn't matter which vector field you pick, you get the same sum of the indices. It's always equal to the degree of the outward pointing vector. But even better, that is the Euler characteristic. OK, so anyway, it's a digression. Smooth manifolds are awesome. And
that's the Euler characteristic of N itself?
That's right.
Okay.
Yeah.
Take 518.
Sorry?
Take 518.
Take 518, yes. Yes.
Where in the book can we read about repellents?
Orientability, you can read about it in the chapter on cohomology. And smooth manifolds, sadly, don't show up in the book at all. But there are wonderful books on differential topology where you can read all about it. OK, how are we doing? Questions on this? So let's see. Yeah. The next topic, so there ends the digression. And so the next topic is to apply degree to homology. So particularly what we want to define next is called cellular homology. And it's when you have a cell complex. So if you have a special kind of cell complex, a delta complex, then we know how to compute the homology, and life is wonderful. If you have a general cell complex, life is not that nice yet. But using degree, we can come up with a complex that computes the singular homology of a cell complex. It makes it no harder than the one for a delta complex. In fact, it reduces to the complex we used for a delta complex if you have that structure. OK? But instead of rushing, I'll stop there.